Welcome back to the deep dive. Usually when we pick a topic, we're looking at things happening on the surface, tech, history, that sort of thing. But today,
Hey, today we're going a little deeper.
literally, we're heading
Yeah.
miles underground to look at magmatic NiQ-PGE ore systems. Now that sounds incredibly complex, but when you dig into the sources, it really reads like a detective story.
It really does. And I know that name, Magmatic NiQ PGE, it just sounds like a mouthful of textbook. It's intimidating.
A little bit, yeah.
But what we're actually talking about is, well, it's the plumbing system of the planet.
And it's a plumbing system that pays out.
Mm.
I mean, we're talking nickel, copper, platinum group elements. These aren't just shiny rocks.
No, not at all. This is the stuff that builds our batteries, runs our electronics. It's powering the future, really.
We can't build a modern world without them.
Exactly. But finding them, that's the tricky part.
And that's the detective part I mentioned.
Hmm.
Looking at our sources today, architectural geometries of magmatic ore systems and foundations of magmatic NiQ-PGE ore systems, I just got this image of the Earth as this giant, chaotic factory.
That's a great way to put it.
It's moving molten stuff around, refining it, and if we're lucky, it stashes it in a safe place for us to find millions of years later.
And our mission here is to understand the conceptual framework of that factory. We're not just looking for random rocks. We're looking for a very specific process.
Okay.
We need to figure out how the Earth takes elements that are usually scattered so thinly, like nickel or platinum, and concentrates them enough to actually make a mineable deposit.
And that really is the central mystery, isn't it? Because the Earth's crust is vast. So why do these valuable metals concentrate in these tiny little spots? Why here and not, 10 miles down the road?
That is the billion-dollar question. And if you look at the foundation source, it deals with the chemistry and the physics, the recipe, you could say.
The recipe, I like that.
And the architectural geometries source that deals with the shape of the container. You need both to work perfectly. If you have the right chemistry but nowhere to trap the metal, you get nothing.
And if you have a great trap but the chemistry is wrong?
You've just got an empty bucket.
Okay, let's unpack that recipe first. Before we can talk about where the treasure is hidden, we have to understand how it's made. The sources say it starts with a mantle source and tectonic triggers.
Right. So everything starts deep down in the mantle, hot, molten rock. This magma starts to rise up toward the surface.
Okay.
Now here's the catch. Usually metals like nickel and copper are perfectly happy just staying dissolved in that silicate magma. They're dispersed, just floating around, completely invisible.
So at this point, it's not an ore body. It's just spicy rock soup.
Hey, spicy rock soup is a pretty good term for it. Yeah, at this stage, it's useless to us. To get an ore body, you need to separate the valuable stuff from the soup.
You got to pull the metal out.
You do, and this brings us to one of the most important concepts in the reading, something called liquid immiscibility.
I highlighted that one. It sounds technical, but the way the source describes it, it's just a separation event.
Think of a salad dressing, a vinaigrette. You shake it up, it looks mixed, but leave it for a minute, and the oil and vinegar separate. They just refuse to stay mixed.
Okay. Right.
In our case, the separation happens between the silicate magma, the rock soup, and a sulfide liquid.
So now we have two different liquids flowing around down there.
Correct, and that sulfide liquid is the key. It's chemically distinct, and it's also much, much denser, so it wants to sink.
Like.
But here's the magic trick. Nickel, copper, platinum, they have a chemical affinity for sulfur. They're what we call chalcophile elements.
Which literally means sulfur-loving.
It does. So when that separation happens, the metals, well, they betray the magma.
They abandon ship.
They absolutely abandon ship. They rush out of the regular magma and dissolve into these sulfide droplets. The sulfide acts like a chemical sponge, just soaking up all the valuable metal.
But the sources say this doesn't just happen randomly. It needs a push, a trigger.
Right. You need to shock the system. The magma is stable until something changes. The source lists three main ways this can happen. First, crustal contamination.
So as the magma is rising, it's melting the walls of the pipe it's traveling through.
Precisely. And if that wall rock happens to be rich in sulfur, boom, you've added sulfur to the mix, you've changed the chemistry, and you force that separation.
So a little pollution is a good thing in this case. What are the other triggers?
Well, you have magma mixing, where two different batches of magma collide. That chemical clash can do it. Or even simpler, just pressure and temperature drops as the magma rises.
It cools down and it can't hold the sulfur anymore.
Exactly. Any of these can flip the switch, and suddenly you've got these little droplets of metal-rich sulfide floating around.
Okay, so we've got our little metal-rich blobs. But then The expert source brings up this variable called the R factor.
Hmm.
I have to admit, when I saw the equations, my eyes glazed over a bit.
Yeah.
But the concept itself seems to be the difference between a pretty mediocre deposit and a world-class one.
It is the single most critical variable for the quality of the treasure. The R factor is just the ratio of magma to sulfide.
Let's break that down because this feels like where the get-rich part of the scheme comes in.
Okay, go back to that sponge analogy. The sulfide droplet is a tiny sponge. The magma is a huge bucket of dirty water with the gold or nickel in it.
Okay.
The R factor is just asking, how much of that dirty water does that one tiny sponge get to clean?
I see. So if I have a huge bucket of water and one tiny sponge and I swirl it around for a long time, that sponge is going to get incredibly dirty. It'll soak everything up.
You've got it. That's a high R factor. A small amount of sulfide interacted with a huge volume of magma. And because the metal prefers the sulfide so strongly, that's the partition coefficient they mention, this sulfide just keeps eating and eating.
And the concentration of metal in that little droplet becomes astronomically high.
That's how you create high tenor or high-grade ore.
Yes.
If the R factor is low, you had too much sulfide for the amount of magma.
Too many sponges.
Too many sponges, the metal gets diluted, you end up with a lot of sulfide, but it's all low grade, it's worthless. You want a greedy sponge and a flowing river of magma.
That is a fantastic mental image. So chemically, we've made the treasure. But now we have a physics problem, right? We have to stop it from just flowing away. This gets us to the plumbing system.
Right. Now we're in the magma evolution and transport section. And we have to remember, this isn't a static pool in a beaker. This is miles underground, immense pressure. The sources talk about magmatic pulses and injections. This stuff is moving.
And these sulfide droplets are heavy, they're metal after all, so gravity takes over. The text calls it gravitational settling.
It's simple physics. They're denser, so they want to sink. But, and this is a huge, but gravity alone is not enough.
Why not?
Well, if they just sink to the bottom of a huge magma ocean, they might still be too spread out. Or if the flow is too fast, the current just sweeps them along, no matter how heavy they are.
So you have to slow the flow down. You need a trap.
You absolutely need a trap. The sources list a few specific structural controls that act as brakes. Things like conduit expansions, change in dip, and thermal erosion.
Let's say conduit expansions. That feels pretty intuitive.
Imagine water rushing through a narrow garden hose. It's fast, turbulent. Now imagine that hose suddenly opens into a wide bucket. What happens to the water speed?
It slows right down instantly.
And when the velocity drops, the carrying capacity drops. The magma can no longer hold those heavy sulfide droplets up. They fall out and pile up.
Like sediment in a river delta. And a change in dip is a similar idea.
Similar principle. If magma's flowing straight up a pipe, gravity is fighting it. But if that pipe turns horizontal, the dynamics change. The turbulence drops and the heavy stuff settles out on the floor.
And thermal erosion. That one sounds a little more destructive.
It is. The magma is so hot it literally melts the rock channel it's flowing through. This creates little pockets, irregularities, maybe potholes in the floor of the channel.
And those are perfect places for the heavy sulfides to get stuck.
Perfect traps, exactly.
But we understand the plumbing, we can predict the shape. And this brings us right to the second source, architectural geometries. This section was fascinating. It moves from abstract physics to, actual 3D shapes.
This is so critical for exploration. As a geologist, you don't have X-ray vision. You have to infer the shape of the beast from the clues you find on the surface.
Okay, let's walk through the big ones. Shape number one, the funnel.
Funnel-shaped conduits. They're exactly what they sound like. They widen upwards, like a champagne glass. The source gives the Jinchuan deposit in China as the classic example.
Jinchuan is massive, isn't it? One of the biggest.
An absolute giant.
Mm-hmm.
And it's hosted in this funnel-shaped intrusion. The magma came up, the pipe got wider, that's our conduit expansion trap. The velocity slowed, and the heavy sulfides settled right at the bottom.
So if you're an explorer, you're trying to find the neck of that funnel.
That's where the best stuff usually pools.
Okay, shape number two. This one has the best name. Chonoliths.
Chonoliths. Sounds like a prehistoric monster, doesn't it?
It does.
It just means a tube-like body. The text is careful to distinguish these from sills or dikes, which are the classic sheets of magma.
Right. I always just thought it was vertical sheets and horizontal sheets.
Nature's a lot messier. A conolith is a pipe, an irregular subhorizontal tube that twists and turns. The source links these to dynamic magma flow.
Because it's a confined channel.
Exactly, like a subway train rushing through a tunnel. And the classic example here is Voisey's Bay in Canada.
Oh yeah, I remember the discovery of that was a huge deal in the 90s.
It was. And Voisey's Bay is a perfect plumbing lab. It has the conoliths, the tubes, and the dikes that feed them. The ore often gets caught where the tube widens. Think of a snake that just ate a big meal.
That bulge in the snake.
That's the trap. That's where the ore is.
I love that image. So you're looking for the bulges. Okay, moving on to shape 3. The reef. These sound completely different. Stratiform sheets.
These are the giants. The Bushveld in South Africa, Stillwater in the U.S. We're not talking about a tube anymore. We're talking about massive magma chambers hundreds of kilometers across.
The source calls them stratabound, meaning they follow the layers of the rock, like icing in a layer cake.
That is the perfect analogy. In these giant chambers, the magma cooled very slowly. The sulfides formed and just settled out in a continuous sheet across the entire floor.
So the Marinsky Reef, for instance.
You can trace that single layer of platinum-rich rock for dozens and dozens of miles. It's incredibly continuous.
So in a chonolith, the ore is in one spot, in a trap. In a reef, the ore is just everywhere along one specific layer.
Generally, yes, it's a different exploration challenge. In a reef, you find the layer, you just follow it. In a chonolith, you have to figure out where the tube zigs and zags.
Right. Okay, shape number 4. Lava rivers.
Linear channels. Now we're going way back in time. We're talking about komatiites, these ancient ultra-hot lavas that erupted billions of years ago.
And the source says these were lava channels and troughs, so they formed on the surface.
Yes, or very close to it. Imagine a river of lava, but it's as runny as water and incredibly hot. It literally carved channels into the ground beneath it.
And the ore is in the bottom of those channels.
Gravity again. The heavy sulfides sank to the bottom of the lava river. They got trapped in potholes on the channel floor. The Kambalda camp in Australia is the famous one. You're basically mining the bottom of an ancient riverbed.
That's wild. Okay, there's one more structural concept the source mentions that seems to apply to almost all these shapes.
Yeah.
The embayment.
The universal trap, yes. This applies whether you're in a funnel, a tube, or a lava river. The ore just loves marginal embayments or footwall embayment structures.
These are just the pockets, the low spots.
Exactly. The floor of a magma conduit is rarely perfectly smooth. It has dips and hollows. The text calls them keel and trough structures. The heavy sulfide liquid just rolls along the bottom and pools in these low points.
So as a geologist, you're basically looking for the gutters.
In a manner of speaking, yes. You're looking for the low spots where the heavy stuff could accumulate and be protected from the main flow.
Which brings us to the final piece. We know how it forms, we know the shapes it takes, but these things are buried miles underground. They're often blind, they don't stick out of the ground. So the detective work, how do we find them?
We have to use indirect clues. We can't see the ore, so we look for the footprints it left behind. This is where geochemical exploration indicators come in.
Back to the chemistry.
The chemistry tells us if the process even happened. Remember the sulfide sponge soaking up all the metal from the magma?
The high R factor, right?
So imagine you're a geologist and you find some cooled lava on the surface. You analyze it. You know that this type of lava should have, say, 100 parts per million of nickel. But your sample only has 20. It's depleted.
Somebody stole the nickel.
Exactly. And the prime suspect is a sulfide body buried somewhere down below. That's called chalcophile element depletion. If the surface rocks are depleted, it's a huge clue that the treasure is sitting deeper down.
That is so clever. You're not looking for the metal itself. You're looking for the absence of the metal where it should be.
You're looking for the shadow of the ore body. We look at specific ratios, too, like Ni versus MgO or Niku. They help confirm if that depletion is real.
Okay, so the chemistry says, yes, a robbery occurred. The nickel's missing. But that doesn't tell you where to drill. You can't just drill random holes.
And that's where geophysics comes in. We try to see into the rock using physics. The source mentions conductivity targets.
Because metal sulfides conduct electricity.
Extremely well. Much better than the rock around them. So you send an electromagnetic signal into the ground, and if it hits a massive sulfide body, you get a big response. A conductor.
You're looking for a giant buried wire.
Pretty much. We also look for density contrast. Sulfides are heavy, so we can measure tiny changes in the Earth's gravity. A big ball of ore will create a tiny gravity high.
And magnetic surveys.
Often these deposits have magnetic minerals associated with them, like pyrrhotite, so they'll light up on a magnetic map.
It really is a multi-layered investigation then. You start with the big picture, the geology, then the chemical clues, the robbery, And then you scan for the physical anomaly.
It's all about convergence. When the geology, the geochemistry, and the geophysics all point to the same spot,
Right.
that's when you bring in the drill rig.
And even then, it's no guarantee.
Oh, happens all the time. You might miss. That's why understanding the architectural geometries is so vital. It tells you how to aim your drill.
So let's wrap this up. We've gone from a mantle source through a plumbing system, separated metals with immiscibility, and trapped them in a funnel or a keel.
And when we finally pull that drill core out of the ground, we see the result. The source mentions the textures: massive ore, which is pure sulfide; net textured, where it's like a spider web around the crystals; or disseminated, where it's just sprinkled through the rock.
My big takeaway from this is just geology is geometry. It's not just what the rock is made of, it's the shape of the container it flowed through.
That's the whole architectural part. You can have the best chemistry in the world, but without the right geometry, without the trap, you just don't have a mine.
Do you have a final thought for our listener? Something for them to chew on?
I do. I want to go back to that R factor and just the sheer improbability of it all. Think about what has to happen. You need a massive volume of magma, a tiny amount of sulfide. You need them to interact perfectly to transfer the metal. Then the flow has to slow down at just the right spot to trap it. And then that trap has to be preserved for 1 billion years without being destroyed.
A whole sequence of lucky breaks.
When you hold a piece of high-grade nickel ore in your hand, something that's, say, 3% or 4% nickel, you are holding the survivor of a chaotic, violent, planetary-scale lottery. The odds of that concentration happening and being preserved where we can find it, it's just astronomically low. It really highlights how rare and fortuitous these deposits are.
A miracle of plumbing. Well, thank you so much for breaking all this down with us.
It was a pleasure.
And thank you to our listener for joining us on this deep dive into the architecture of the underworld. We'll catch you on the next one.